Okay, let's look at another approach. So this will be called hash tables with separate chaining. So this is an alternative to open addressing, and basically what we're going to do is we're still going to use an array, but it won't be the simple array that we used before. So instead of the simple array, we are going to allow each index of the array to contain multiple items. That way, when the collisions occur, we can just put multiple items in that same location. So we'll use the term bucket to refer to these locations. So we've already seen the term bucket when we were talking about bucket sort. So the basic idea is it's a container that can contain multiple pieces of data. So how can we implement this? Well, we'll talk about one specific implementation, and it's one of the more common ones. So one option would be to use a linked list. So essentially all of the items that are put in the same location end up being added to a linked list. And this linked list actually ends up behaving like something we've seen before. It looks like our first variation of doing maps. It behaves somewhat like the unordered list-based map that we already saw. Okay, so let's go through our example again. We'll do several inserts, several puts into a map, and we'll look at both successful ways of selecting locations and things that lead to collisions. Okay. So once again, we have an array. In this case, the array contains this idea of buckets, linked lists that will contain the data that is actually going into that particular location. So we'll go through the same set of puts that we went through earlier when we first started talking about the open addressing approach. Okay, so we'll put an orange in container 3. And I'm going to go through this pretty quick because we'll see a very familiar pattern. A lemon goes in 7. Calendar will go in 8. Light bulb goes in 1, baseball goes in 0, and a bear goes in 4, a mouse goes in 6, an eraser goes in 2, and finally a pencil goes in 5. Okay, so we've done a whole bunch of puts. We've put data in our map, and now we're going to see if we can get a bear. So we'll go to bucket 4, and we'll look in bucket 4. There's only one thing in there, and it happens to be a bear. So if we distribute these things somewhat evenly, like we did with our first example, everything works out great. So now let's take another look at the example where we start running into collisions just to illustrate the difference between these two. Let's go through our process again, but this time the thing that tells us which locations to use is going to perform poorly. So we'll go through our puts. So we'll put the orange in location 3. I'm going to draw the diagram just mildly different this time. So I'm going to put the items down below the bucket. And because they're going on a linked list, I'm going to kind of show them like nodes being connected together. So if there's something down below the orange, we'll show a little linked list arrow connecting to it, which we'll get to in here just a second. So the lemon would go in box 7. So if we want to put a lemon in here, we'll put it in box 7. And now we'll put a calendar in 3. So this is where we have a collision, and we'll indicate that with kind of a node in our linked list here. Now we'll put a light bulb in 7. So again, there's a collision. By the way, if you remember when we talked about the unordered list-based approach, every time I do a put, I actually have to look at everything that's currently in the unordered list to see if I'm doing an update versus adding something onto the end. So this isn't as simple as just doing an append. So we'll be a little bit clearer about that as we add our third item, a baseball. So baseball belongs in bucket 3. I need to look and make sure the baseball isn't already in there. If it were, I'd update its value, but it's not, so I append it on to the end. Okay. Okay, so next we'll go ahead and insert a bear at 7. Again, I'll go through and confirm that the bear isn't already there, and since it's not, we'll append it onto the end. Okay, so let's think about what happens if we want to look something up. If we want to find out if there's an orange in this data structure, we know that an orange would belong at location 3. We would go out to the bucket, and we're lucky. It's the very first item in the bucket. We get it almost instantly. But if it's the last item in the bucket, we may have to go through everything in there. And if our locations are particularly bad, if for some reason we put everything in the exact same bucket, this implementation will behave essentially like the unordered list implementation. By the way, the linked list nodes here probably give you some idea why this is referred to as separate chaining. We've essentially got separate chains for each of the possible locations in our array. So while we're here, let's also talk about time complexity. And we'll start off by thinking about the best possible case, which depends on that process of finding the location of something being really, really effective. So we'll assume that no collisions happen and that our array size is bigger than the amount of data that we're going to be storing in it. So we'll compare this with our previous two implementations, the unordered list and the ordered array. So our put operation for the unordered list was n. We had to go through all of the items and see if it was already there and possibly update it. The ordered array, we may have to shuffle everything around. With open addressing, it'll be constant time. Our process of identifying location will tell us instantly where to put it. The array has random access, that random access property, which allows us to assign a value to an array in a constant amount of time. This is also true of separate chaining. It's just that instead of a simple assignment to an array, we'll add it onto a list in an array. And if we're assuming that each item is only assigned to one location, or each location only has one item assigned to it rather, then we're appending onto a list with nothing in it, and it'll essentially be constant time. So the get operation, the unordered list, we had to go through everything. The ordered array, we could do it in log base 2 time by using binary search. With open addressing, we'll know exactly which bucket it should be in, and we will go directly to that bucket in constant time. The same is true with separate chaining, although the bucket's a collection itself. If we're assuming that we have no collisions whatsoever, each bucket will have a single item in it. Okay. Remove operation is essentially the same sorts of arguments. The unordered list, we had to go through everything and find it. The ordered array, we had to find it and then shuffle everything over to cover up the removed item. Open addressing and separate chaining, both will go directly to the location. There will be nothing there, and we'll essentially be able to remove things in constant time. So that's the best case. What about the absolute worst case? So let's assume that everything is a collision. And we'll assume that we're using open addressing with linear probing. Again, there are other approaches other than this linear approach to resolve collisions with open addressing, but we'll just focus on that one. So the unordered list and the ordered array were both order n for the put. With open addressing, we may have to go through the entire array, which, again, we'll still assume that the amount of data is less than the available positions in our array. So we may have to go through all n items that have already been added to the array. And with separate chaining, we may have to go through all of the items that are in the bucket. And if all of the items end up in the same location, it will essentially be a linked list that we'll have to iterate through and go through all n items. So get with the ordered list was order n. I'm sorry, the unordered list was order n. The ordered array was log n. And with open addressing, we may have to go through that linear probing process and find something, and we may have to look through all of the pieces of data that have already been added if everything resulted in a collision. Same is true of separate chaining. So the remove, essentially the same sorts of arguments. We may have to go through everything that's in the list or the entire array. Okay, so let's also talk about space utilization. So we're still going to use n to represent the concept of the number of items that we're storing, but now we'll introduce a new variable k that represents the number of buckets or the number of array indices. So thinking back to our unordered list, it doesn't use an array whatsoever, so it will just store all of the data that we put into the list. So if we add n items, it'll have a total of n units of space being used. The ordered array, we create the array, and I'm going to assume here that n is less than k. So we've created all of these buckets, and we have enough space for all of the items that we'll ever add. So it's the number of buckets that's going to determine the total amount of space used. And we'll make the same arguments for open addressing. We'll assume that we have enough space in our array to accommodate all of the items we might add. So we'll assume it's order k space. Separate chaining, we actually don't have to make that assumption. We could have fewer buckets than amount of data. So it would be, we could think of it maybe more precisely as the sum of these two variables, and whichever one dominates will actually be the one that controls our space complexity.